Good day to you. This is Galactic bringing you another science presentation in a new series which will run through the equinox. It is projected. This is only the second day of our new series, and I've been off for about 2 weeks, not producing. The first time I've gone more than 2 or 3 days in producing a lecture in 2 years. The reason for that was several things I've covered. There was a certain financial strait which has been overcome, and certain other, I'll just say, things going on in life that every now and then you have to interrupt your work, whether you like it or not. I did not like it, but it was important, it turns out. Everything is connected, and there are reasons for things that sometimes we don't perceive at first. I am a man of faith, so I do believe that I can't see everything into the future. But there are reasons for things that we consider to be troublesome or a tragedy of some kind. Later on, after gaining some perspective on what happened, you find out that there was a reason. Now, it may not fully explain the tragedy. Also, good events, boons, are later looked upon as not necessarily having been a pure blessing. So nothing is a pure blessing or a pure curse at the time of encounter, because you don't have proper perspective to see everything that's happening. We're quite finite beings. Well, that's a basic principle of science. Again, I apologize for my voice because of the recent heat wave, which is continuing through today. It'll be in the hundreds again today. It's affected my asthma. So I'm not actually sick, but I may sound a bit strange, so I apologize for my voice. Today, we're going to cover quite a bit of ground rapidly in order to gain an overview of the importance of the number 2. It's a synthetic sequence in the sense of unifying, broadly speaking, bringing into the same arena certain concepts which all have something in common. So I'm just going to begin because really the examples are going to explain themselves, but I'll be narrating this more or less. The Boshkovich force curve is a major topic in my curriculum now, but that was not always the case. The Boshkovich force curve, I must now define for you. You may know what it is, certainly if you've heard some of my previous presentations. But to sum it up, it's always very important to summarize in science. It's a two-force symmetry that explains physics at the dynamic level. So it's quite fundamental. Naturally, this runs up against current modeling, but it's very important to understand the nature of modern scientific modeling. Here I should give at least a couple of examples of what I mean by modeling. There is a cosmological model, there always is one, that men use to talk about their perception of the entire universe as a thing, which is quite difficult to do since it has no known boundary and no known center. So we do have a cosmological model that's dominant now, and because of the nature of communication now, a very rapid and massively networked communication, a model tends to be overblown by repetition. And this is dangerous, so you should be aware of the pitfalls of modeling. There's always some kind of guideline behind a model. It has presuppositions, what we call an axiomatic basis, if that has been acquired. And that can be done incorrectly, and of course no cosmology has ever been correct. So it would be quite unlikely if the current one were correct. So there is a pitfall there because of the incredible emphasis on this model. It's in all the classrooms, in all the grade schools, certainly in high schools and colleges. There's this funnel And you've seen it. You're not allowed not to have seen it. You definitely have seen it. It's required that you know what this model is. And you certainly know of it at least by name as the Big Bang. Well, the Big Bang is part of a model. And of course, it's the most celebrated part because it purports to describe the origin of the universe. The reason for this model is important to understand if you take it seriously. There's no real reason why you should take the standard model of cosmology seriously. Even if there's a grain of truth in it, it doesn't make any difference. Now, to the modelers, it does. These are plasma physicists. They're subatomic particle physicists. They're high energy physicists. They're all physicists who come up with this model of the universe. And it's based on essentially another model called the Standard Model of Particle Physics. The Standard Model is so advanced and fleshed out now that it has a life of its own. But it's another model that you really need to examine the axiomatic basis. In order to get to the axiomatic basis of a cosmological model, such as the current, it's really an expanding universe model. And it's the expanding universe idea that leads one to an extrapolation called the Big Bang. By winding back the expansion, you reverse time order to project backwards. From an expanding universe, you can contract it back to a Big Bang. That's the premise. But the way it's fleshed out so that it becomes a model that appears to be useful to astrophysicists, they use this model to explain, for instance, galaxy evolution, supermassive black hole phenomena, and the CMBR, several aspects of astrophysics and quasars are modeled according to this guiding framework model, which is biased, obviously. So that's the danger of a model, is then that by looking at macro scale objects, such as supermassive black holes, quasars, CMBR, these are interpreted according to what's already assumed to be the correct model. And that leads to enormous errors, which are rampant now. So the entire cosmological model is essentially a misguiding effort based on false premises. Now, I've covered that, and you may agree or disagree with that, but that's why I began by saying it doesn't really matter. There's always a cosmology. But the standard model of particle physics is quite psychotic. The reason being is its axiomatic basis is well laid out. You can look in Wikipedia or any other source. I've checked several sources over the past few years to make sure that I understand what they say they understand. And it's patently obvious why the standard model of particle physics is fully accepted by those who need to use it. It's because of their avowed goals. These are particle physicists, of course. High energy physics, subatomic physics. Well, you know what that's for. Historically, what that's been for, you could say it's for technology. You could say it's for the advancement of the quality of life of humans. That would be the good goal of science. But there is obviously always the government wants these scientific discoveries in order to gain power. It's a sordid and nasty side, and in polite conversation, it's kind of an intrusion to bring in this just a nasty, sordid aspect of science. That its for main purpose is for the mass production of massively destructive weapons. So these men are paid by the government to have a certain perspective on things, and they just want jobs. So the industry drives itself. But that's where we get this one-sided model of particle physics. There are now, I keep checking over the years, I keep checking to see how many particles they think that they've identified. You have to understand what these so-called particles are. Muons and pions and gluons, and of course everyone has heard of the Higgs. The Higgs is an amazing thing to try to even understand. And of course, I've made it my job to understand it, but it was not a pleasant thing to do. Now, what I've done through a process of synthesis in order to present to my listening audience, whoever that might end up being, a correct perspective on the standard model of particles, it premises itself this way, and I'm simply quoting from the authorities, that everything in the universe is a particle. But obviously that can't be true, because there are such things as forces, such as gravity. Well, you'll find in the list of particles, the graviton, it's in parentheses, or, there's a notation that it hasn't been discovered yet. But they know it will be, because everything is a particle. So there are two classes of particles in this model. You may have heard of the bosons. Well, the bosons are one of the two classes of particles. There are only two. There are bosons and fermions. The nomenclature is a little bit confusing, and I don't want to make this confusing. I'll say this. There are two major classes of particles. In other words, it's a tier system. And there are two types of particles according to the model. Well, one of them, the bosons, are the force carrier particles. In other words, forces are not what Newton conceived as forces. They're particle mediation. They're particle activities are the causes of forces, that they're mediated by particles. Well, I'm just going to tell you that is simply not true. That is in reality. So why would these physicists say something that's so obviously untrue? It's because their mathematical system guides them to framing things this way. It's useful to their industry to look at the universe this way, as being as if it were made of particles. Now they, in their inner circles, and of course this is projected onto the public, they consider all of these things to be perfectly real. They're not. They're not. And the reason we know that this model is wrong is because there is another part of science that has a much better model, where things are not all particles. And that's resurfacing. It's actually a 250-year-old theory, which was invented by a man named Roger Bošković, who followed right on the heels of Leibniz and Newton. As they were departing this world, Bošković was entering it. So he's the successor of the two discoverers of calculus. So our first introduction in this swift review of the value of the number 2 in coordinating our view of modern physics, modern science, this number 2 will become quite useful. It's particularly useful from my perspective because of what I discovered in geometry. So let's go through this quickly. The Bošković force curve describes a dynamical system that explains the atom. This is known. He's never been refuted. Nobody has ever found a flaw with Bošković's theory, which he spent the second half of his life working on practically exclusively. So he wrote several treatises on this, and his most important work, according to himself and everyone else who's read it, I have read his book, Theoria Philosophiae Naturalis, which is Latin. He wrote in Latin. But it has been translated into English. A very fine edition that you can get for free. You can download it from, I believe, Gutenberg. The site called Gutenberg.org has it. But if you look for Theoria Philosophiae Naturalis by Roger Bošković and put in PDF in your search, you'll find it, and you'll be able to get this book for free. I'm not saying that you're going to want to read the whole thing, but it's amazing that even though he was a master of Leibnizian and Newtonian calculus, he did not actually use it. In his theory, he didn't need it, and here's the reason. He used the number 2. He figured out that Newton did not quite get the entire dynamic system that science would like to have. That Newton only saw a very small part. Well, a very large part in another sense. Gravity. Newton had a very, very good formulation of gravity using the calculus that he essentially developed for this reason, was to get a better formula for gravity than Kepler had gotten, and Kepler made a major breakthrough in his formulation of essentially the geometry of planetary orbits, or solar system orbital system, including the moon around the Earth and the planets around the sun. Kepler formulated a very good mathematical equation to describe that, and Newton was thought to have perfected it. However, Roger Bošković, after both Leibniz and Newton were dead, Bošković came on the scene and was the foremost scientist in Europe following the deaths of those two men, and also Christian Huygens had died just a little bit earlier too. So really, Roger was the uncontested master scientist of Europe following the deaths of the previous generation of scientists. So what he said in his book, very explicitly, in great deference to Newton, whom of course he respected enormously, but he also pointed out quite clearly that Newton was wrong, that Newton did not get it right. He did not get the full dynamical system of the universe. He only saw gravity. He did not see that there had to be another force to balance gravity, which is a remarkable thing to be able to say now, because Newton is quite famous for his principle that he stated in such a memorable way, that for every action there must be an equal and opposite reaction. That's known as the law of conservation, and usually it's called the conservation of energy, but it could also be called the conservation of force. In other words, there's a balance. And it's remarkable that even though Newton is famous for having published this principle in his famous book, Principia, But it's known to school children that for every action, there is an equal and opposite reaction. Well, to this day, mainstream science appears totally unaware of what Bošković said after Newton, which is that the attractive force that Newton was describing, gravity, of course, is an attractive force. It's not repulsive. But if it's a force, there has to be a counterforce to balance it. Otherwise, there is an action of centripetal force, which we call gravity, but with nothing to compensate it. This actually has a direct impact on the interpretation of the supermassive black hole, which is considered to be the largest gravitational entity or phenomenon, the largest gravitational object, we would commonly say. It's not certain that it's an object either. But if it is an object, and it certainly can be conceived to be that until we have better information, it would be a protonic object, that is, a gravitational force object, exerting a force called centripetal force, which draws everything to its gravitational center, which leads to a perplexing situation, is that you have to ask yourself, as a scientist, a physicist, or just someone trying to figure out what is gravity? What causes gravity? What is gravity? Well, Newton had a formula for it, and now we know that Einstein has what's considered to be a much better formula because of the introduction of relativistic corrections, which is only necessary really for extremely high speed, close to the speed of light. Then you need relativistic conversions. But this formulation of gravity is still what Newton said. Basically, Kepler, Newton, and Einstein all worked on this single force called gravity. Well, we now know, although it's not commonly stated, that gravity must be explained at the atomic level as the combined force, that is, the integral force, the field force of a mass of protons, which is somewhat redundant in the sense that protons define what mass is. But massive, like the Earth or the Sun, any cosmic object, such as a planet or a star, is a gravitational object. Well, what holds it together? Well, you can say gravity, but you do have to ask the cause of gravity. Well, it is the protons. But that still doesn't answer the question fully. How are the protons causing gravity? Well, we can now state it in a better modeling form after Einstein. And this is fully supported by the experts in the area. This is not me just making up a model. I'm simply stating what is now said about gravity, that it's actually best perceived and explained as the curvature of space. So space has a quality, according to Einstein, that it can curve. Well, that means that something is changing space itself, correct? This kind of takes the place of spooky action at a distance, because it's not as spooky if you can state that it's due to the curvature of space. But you can see this leads to a recursion. A recursion occurs when, for instance, you explain something, but it immediately introduces another question. This is quite common in science, and it's part of the mystery of reality, that we're trying to explain phenomena that obviously require an explanation. Well, that's called mechanics or dynamics. Some explanation, for instance, for magnetism, or an explanation for why electrons go around the proton, or an explanation for the force of gravity. This is very, very interesting, to the degree that even such remarkable modern scientists such as Dr. Sabina Hassenfelder, whom I respect enormously, and I recommend her video series. She's a YouTube presenter, and she's written a few books that are very well worth reading from everything that I've heard. Lost in Math. Now, I have a book called Love and Math. Mathematicians can be poetical if they want to. And in fact, John Archibald Wheeler, a Nobel Prize laureate in the field of space-time, essentially, so one of the foremost modern authorities on space-time, John Archibald Wheeler, wrote a whole poem, over 100 pages of essentially gushing adoration of space-time. And yet, it's so remarkable that it's a single force, contradicting Newton, that there must be a balancing force to gravity. Well, have you ever heard anybody talk about it? That there has to be a balancing force, an equal and opposite force to gravity. Have you ever heard anybody suggest that that should or must be the case? Bošković did. At the atomic level, he discovered that in order to explain particles, before particles were even discovered, Newton talked about particles. Well, Bošković followed up on Newton's work. And what he was most concerned with, believe it or not, and so were the physicists of his day, they were vitally concerned at a totally basic philosophic level of what happens with matter that holds it together, for one thing. What holds matter together? Matter being conceived as particles, which turns out to be correct. But there are two particles, and only one of them is matter. The proton is the source of magnetic force. It's centripetal force, which manifests as the so-called Coulomb force, which is simply the charge relationship between the electron and the proton, is called the Coulomb force, which is an electrodynamic interpretation based on plus minus, which is a two force system. So electrodynamics does have a two in it, but gravity does not. And yet gravity is essentially the combined force of protons. That both explains why a star such as the sun holds together. It's due to the integral force of the protons. So it holds the protons together, but the way they're doing that is by their separate field effects. A proton exerts a force in space that bends it. That's what Einstein taught us to visualize, and I believe is perfectly reasonable. But if you say that, it means that space itself has a quality. But it also is saying something else, that something is acting upon space. That would be the protons. Well, what that implies then is there has to be an equal and opposite force. Ruđer Bošković discovered that at the atomic level, which is quite a remarkable accomplishment, considering the atom had not been discovered, and neither had the electron or proton. Those would not be discovered for over a century after Bošković's day in the sun, when he wrote this book, and then passed the way of all men, passed off the surface of this planet, and we only have his book left. and his other writings. But nobody has ever entered Roger Boshkovich into any curriculum that I've ever found. His name, until very recently, was virtually unknown. Now Tesla knew about Boshkovich's work, and so did Faraday, and it's safe to say that physicists in general would have known about Boshkovich's work. He was basically the foremost science in Europe following Newton, Leibniz, and Huygens. So he's a major character. He had no real rivals either. So it's remarkable that his work was forgotten almost completely, but recently, within the past, I'll just say, few decades, his work has come back up because it turns out that his force curve, which is a two-force system, gave him the ability to draw the exact curve that you'll find in Wikipedia for the strong force. So he fully explained the relationship between two particles as being due to two balancing forces, only one of which pulls in. The other one has to be repulsive. Well, you would have to really rack your brain, I think, because it's not stated in any textbook anywhere, not even as a footnote, that Boshkovich said there has to be a balancing force to centripetal force, to gravity, to protonic force, to magnetism. All these are the three manifestations of centripetal force. At the atomic level, it's the proton. At the macroscale level, it's gravity. And in between, due to the electrodynamic relationship between protons and electrons in molecular systems, such as a bar of iron, for instance, that certain metals will induce what appears to be a gravitational force because it pulls in. But then you know that magnets also exhibit repulsive force. They will repel each other if their poles are the same. North repels from north and south repels from south. These are dipoles. They're not monopoles. They're not freestanding in the sense of having a center. A magnet does not have a center. Unless you think of the center as being elongated, which is no longer what we would call a spherical center, but it would be a locus of balance. And so magnetism is an in-between phenomenon. It doesn't manifest a spherical system such as the proton, the nucleus of an atom, produces a spherical system. Well, then we find at macroscale that gravity also induces a spherical phenomenon. Both the star itself will be spherical and the gravitational field is spherical. So at the macroscale and microscale, it's spherical. But magnetism is not spherical. So it's quite interesting that these are the three manifestations of centripetal force without a balancing force. And as I began to say, even so esteemed and very well informed scientists such as Dr. Sabine Hassenfelder, who works in quantum mechanical experimentation these days, is what she's doing, as well as producing on YouTube, quite an industrious and really amazing woman. I really respect her. But she gave a whole presentation where she said just a little too emphatically, just a few too many times, I never trust someone who says something too many times, because it sounds like they're trying to convince you of something that perhaps requires that emphasis because it might not otherwise be believable. The Big Bang was promoted this way. natural selection was promoted this way. You just keep saying the same thing over and over again until people get used to it and they stop questioning it. Well, she, in my opinion, indulged in this in her presentation, which was simply to state, and it's in the title of her video, you could look this up and listen to it. She says that gravity is not a force. Well, she's not alone. She's on very firm ground. But there is a division of opinion among physicists on whether that's a true statement. It's about half and half, as far as I can tell. That nobody's sure if gravity is a force or not. And the reason is you can either look at it spatially or not. In other words, if you think of it as Newton did, that it's a force without any relationship, it's just a force. Well, then you can't think of it as a force, because that would be an action for which there must be an equal and opposite reaction. Well, we don't see any. Gravity is static. There's no motion. So it's thought that it's not a force because there's no manifestation of energy. Energy, of course, is measured as motion. There's no such thing as energy without motion. Very important insight, by the way. But space is thought to be bent. It's a legitimate way of looking at things, although you have to realize it is a visual interpretation of something you can't see. So to say that space is curved is now in vogue. I accept that. It is a reasonable thing to say. But now you're faced with an enormous question. It's a recursive question, as I pointed out. You have to explain what is bending space. What is bending space? Now, the way it's shown, usually, in a 3D projected diagram on a page, I've seen this countless times, and I'll bet you have too, that to explain the curvature of space-time, which is why this is done, you'll see a BB or a ping pong ball or just some little sphere on what looks to be a trampoline, right? And the trampoline is bent so that the ball makes a curved, essentially a hole in space where it's curved in. Well, that's representative of the force of gravity, but it's being shown visually as the curvature of space, which is simply another way of looking at it, but it is a force that's causing the curvature. How? Well, visually, the whole issue is dismissed visually by showing and then explaining in the caption what you're seeing. Yeah, always a dangerous thing, but this is how we try to communicate, so it's a reasonable effort. That this trampoline is bent. So that's the stretching of space. Well, that is due to a force. It's just static. There's no motion. You see the effect of gravitational force when something moving comes within measurable range of the gravitational field, and then its change in direction can be measured due to the curvature of space. So the question is, what is causing the curvature of space? If you say it's the proton, I would say that you're correct, but now comes another question. How is this little tiny BB bending the space around it? Well, we can describe it as a force field. That raises the question again, well, what is generating the force field? If you say it's the particle, that's not a mechanical answer. It's just a statement of identity. That because the particle is there, there's a force field. So you're not answering the question, what is causing space to curve? Because electrons don't do that. They don't cause the space around them to curve. They don't generate a centripetal force field. So the question is, what is going on inside the proton that's giving it this power to bend space? That, if you would, is the reason for the hadron colliders that used to be called cyclotrons. Now, of course, there's a sordid side to this, that they're trying to get another weapon. Of course they're trying to get another weapon. You just have to turn a blind eye to that. Because we do get benefits from this military research, which is all the hadron colliders are. They're military installations looking for the next super bomb. That's played down because it has another purpose. It's a new power source which would benefit humanity potentially. So there's a good side and a dark side. But the scientific side is we're trying to explain it. We want to understand it. You can't really harness a source of energy unless you know how it works. So this has to do with what's called the strong force. Because protons will bind together, which is strange, because normally they repel. They both have, in the electrodynamic formulation, they have a positive charge, well known, in relation to the electron, which then would have a negative charge. So, in that sense, the two-force system appears in the atom. But now when you look at gravity, there is no equivalent to the electronic balancing. There's no plus minus in gravity, it's just all plus. Well, where's the minus then? If space is being bent by a star such that planets will go around it, that is the situation. Newton described the force of gravity as causing acceleration. Because this planet is not going straight, it's going in a circle, there's a force holding its motion to the circle. That's why the solar system is fantastically stable, because this circular motion persists. Well, the point of Newtonian mechanics is there is a force causing that. You cannot just say that space is curved like that's the most natural thing in the universe. Although in a way it is. It's just the most natural thing in the universe. That the space around a macroscale object such as a star, such as the sun, it has a gravitational field. Well, that means that there's a force which can be shown by the motions of the planets. If there were not that force holding the planet to its circular orbit, it would fly straight and it would not be affected. The planets would just fly away on a linear course. And the reason they don't is because they're being accelerated. So it's a permanent form of acceleration, which means that there is an energy source. Well, the proton does not appear to be an energy source, but you have heard that mass is equivalent to energy by the formula E equals mc squared. So the proton is, for that reason, a manifestation of energy. How? Again, this is recursive. So what we've been trying to do ever since the discovery of the atom is find out what's at the center. Well, we found out it's a mass of protons, as many as 100. The periodic table is simply a list of 1 proton, 2, 3, 4. Each one of these is an element. Elements are defined by the number of protons. which is a finite sequence. You can't get more than about 120 protons together, because then they start to fall apart by themselves. They won't hold together, they just disintegrate back into smaller units of smaller numbers of protons. But uranium, I believe, is 92, and you don't get too many more after that. Plutonium, I believe, is the next one. Neptunian is in there somewhere as well. And then there are a few which are highly unstable, much more unstable than uranium and plutonium. They just basically can be made in the laboratory, and then they don't last very long. So that's the nature of a protonic core, what we call the nucleus, which also can have neutrons, which, by the way, I've given several presentations on why there is such a thing as a neutron. Oh, what role does it serve? Well, it's quite interesting. But it's essentially a proton. You could say in electrodynamic language, it's a proton without a charge. It's exactly the same weight. There's no difference between a proton and a neutron, except what we call the charge. Well, that means that the proton is an energy. It's a manifestation of energy. The fact that there's a difference between the proton and the neutron shows that the proton has a capability, and the way we think of that, according to the diagram of the Bohr atom, is that it's exerting a force field of centripetal force that the electron responds to. So if you're interpreting the atom in a space-time sense, then you could easily see in the Bohr atom that the proton is bending space. In the case of a hydrogen atom, it's typical, and I'm not the only one who does this. You don't want to just keep saying the nucleus, because that could be 1 to 100 protons with all kinds of isotopes and neutrons. So you have all these footnotes. But essentially, the matter is quite simple. When you're dealing with one proton and one electron, it's called hydrogen simplex is one way. It's hydrogen without any neutrons. It has, there are isotopes of all the elements, and it varies the number of neutrons that can be added to a nucleus. So essentially we have the proton bending space. Rather roundabout way of saying all that, but that is what it means. The proton creates a force field in space. Now, in a gravitational body, it's the integral of all the protonic force which is bending the space around the planet or star. That's rather simple, I think, and it makes sense to physicists, and it makes sense to me, so I hope it makes sense to you, because then at least we're all on the same page in what we believe we're seeing. It is the curvature of space. So that means there's a force, which comes from the proton. Well, that means there has to be an equal and opposite reaction to that force. So where is the rebound? Space is being pulled in by something. Where is the reciprocal force? Where is the centrifugal force that explains that? Well, we know that it's got to be inside the proton. And so we built cyclotrons, which are now called hadron colliders due to this standard model, referring to protons as hadrons. And the effort is to smash them together to see what flies out. That's really what Leibniz, Newton, and Boschkovich were talking about at a scientific, philosophic level, and each of them had a slightly different view on what happens when two particles collide. So the Hadron Colliders are executing experiments which These men would have given a lot to be able to know what happens when two particles collide, because there's a paradox involved there. Are they indivisible particles such that when they collide, they do what? Do they bounce off each other? Do they interpenetrate? Do they explode into little pieces? Well, a proton will explode into little pieces. And these are the so-called particles. I hesitate to call these things particles because the proton is the smallest particle. In, I'll just say, traditional modeling, when you say particle, you're talking about a proton because it makes a center in space. Well, that would be a pretty good candidate for a particle. So we try to measure it. How big is it? How small is it? But we know a proton is under a femtometer in radius. A femtometer is the smallest useful measuring unit in subatomic physics. And I could give you some marvelously overwhelming number that is a very, very tiny distance, of course, very close to the Planck limit. So it's at the limit of measurability. Well, you would expect so. It's the tiniest thing. Well, actually, that can't be quite right. It's got to be a mechanism. There's got to be something happening. It is a manifestation of energy. We do know that. But it doesn't behave. For instance, the electron is obviously energy, which even has a paradoxical aspect. Is the electron actually a particle? Well, that's 52 minutes, and I think that's enough for our discussion of the number 2 here. This is probably the most profound aspect of my presentation sequence. My geometry, of course, is what I'm trying to present, which is based on the number 2. And it's quite explanatory, but it turns out that there is a resonance throughout physics from the bottom up, that this 2-ness just keeps reappearing at the paradoxical limits, that it always ends in some kind of 2-ness that we can't go beyond. One of those is the 2-force system that describes atomic dynamics. And Bošković discovered that before the atom was discovered, because he was attempting to explain what happens when two particles collide. And he got it right, but physics has not realized yet that he got it right. So you're tuned into the right station for getting cutting-edge real science, because this is a major, major breakthrough in physics that has not yet come to the attention of mainstream physics. So to the degree that you understand the Bošković 2-force system of atomic dynamics, you'll be ahead of all the physicists. You will understand physics better than they do. That'll be in the next presentation, because I want to keep this under an hour, and I'm also losing my voice. So that's our Roger Bošković 2-force symmetry that explains everything. And I haven't even told you the answer yet. Where is the centrifugal force? I think you can guess. Is there anything in the universe that just goes out? Because gravity just goes in. It bends space in. It never does the opposite. Gravity, due to protonic integral force, always bends space inward. Well, that means that something has to bend out somewhere to compensate. That's actually part of the nurture force, the symmetry. It's a form of conservation of energy. That if there's gravity, that's a centripetal force pulling in. There must be something pushing out somewhere. Well, that's light. Light is the only centrifugal force manifested at this level. You could say a merry-go-round, or if you swing a bucket of water, Newton is famous for this. You swing a bucket of water on a rope, the water stays in, and it's because of centrifugal force. That's actually quite mysterious and difficult to explain. And Ernst Mach, had a very interesting point of view on what centrifugal force actually means. It is recursive, so you can really get deep. But what we want is understanding, which is it's a balance to get understanding. In probing the limit going in, though, this is what we've reached. It appears that the electron is the manifestation of centrifugal force, but the proton is the manifestation of centripetal force. And the problem in each case is somewhat paradoxical, because if the electron is centrifugal, what holds it together? And if the proton is centripetal, what is causing the force field? Spooking action at a distance, although a tiny distance for a proton. For a planet, it's a bigger distance because it's a field effect. So there's a balance between the field effect force and the other force. And Bošković was the first man to notice that, and physics has not yet caught up because it's somewhat blinded itself. So that'll be in the next lecture. I hope you enjoyed our very brief introduction to the Bošković two-force dynamic explanation of the atomic system, which is balanced on two forces, not one. All right, so this goes to the definition of light and the definition of gravity. That's called the unified field theory, which is considered to be the most coveted solution not yet found. I've got it. This is it. This is the unified field solution. Absolutely rigorously mathematical and geometric, totally explanatory. But it involves, obviously, there's something preventing physicists from noticing this fundamental symmetry. What is blocking the view of physicists in perceiving the two-force balance system, which would explain both gravity and light with one equation? What's preventing that direct perception? We'll cover that later, but food for thought, something you might want to think about. And this is Anagalactic, bringing you the secrets of the universe in our Equinox series, now that we're in high summer. Today is June 22nd, a Saturday in Chico, California. I'm glad to be back. I was actually exhibiting some neurotic behavior, which was noticed at my local cafe where I hang out almost every day. And I was showing some signs of elliptical behavior because I'm so involved with making these videos now that I actually get upset being away from doing it. So I'm kind of addicted to doing this. It's so much fun. I'm glad to be back. So stay tuned and keep looking up at night. That's your best time you'll spend on Earth, except here at Anagalactic, where you're going to get the secrets of the universe that'll blow your mind and undo your bind. We'll be right back.